All right, let's jump right in. When we think about how machines learn, we often start with simple models that make these hard yes or no decisions. But the real world, it's messy. It's not always black and white. And that's why today we're talking about logistic regression. It's a seriously smart upgrade that teaches machines to think in shades of gray, and that lets them make much more nuanced predictions.
And this, right here, this is the core of the problem we're trying to solve. I mean, think about it. If a simple algorithm like the perceptron gets something wrong, its only feedback is, nope, wrong. But how wrong was it? Was it a near miss, or was it a completely wild guess? That all or nothing feedback makes learning kind of slow and clumsy. So how do we fix that?
So here's the game plan. We're going to start with that all or nothing problem. Then we'll introduce a much smoother way to make decisions. After that, we'll look under the hood to see how the model actually learns from its mistakes. We'll even see how to go beyond simple two-choice problems. And finally, we'll get real about its strengths and its weaknesses.
Okay, first things first, let's really dig into the issue that started this whole thing. It all goes back to a simpler algorithm, the perceptron, and its really rigid, kind of inflexible way of learning. Check out the difference here. It's pretty stark. On the left, you've got the perceptron with its hard updates. It's totally binary. A prediction is either 100% right and nothing changes, or it's 100% wrong and it makes this big, clumsy adjustment. That is just not efficient. But then look to the right. Logistic regression uses soft updates. It gets this continuous feedback on exactly how wrong it was. And that right there allows for way smoother, more precise, and just better learning. So how in the world do we get those smooth, intelligent updates? Well, the answer is actually in this beautiful little mathematical tool that sits right at the heart of the whole algorithm. Let's see how it works. And here it is, the hero of our story, the logistic function. You'll often hear it called the sigmoid function, and that's just because of its distinctive S shape. Its job is incredibly important. It can take any number you throw it at it, positive, negative, huge, tiny, and it just gently squashes it down into a value that is always between 0 and 1. Now, you're going to see this formula, but don't let the symbols freak you out. That part inside the parentheses, that's just the model's internal score for whatever it's looking at. And that little sigma symbol, sigma, that's our S-shaped logistic function. So all this thing does, the whole point, is it takes that raw score and turns it into a confidence level, a number between 0 and 1 that acts a lot like a probability. And this quote just nails the payoff, because the output isn't a hard 1 or 0, but a soft value like, say, 0.8, we can measure the exact size of the mistake. If the right answer was 1, the error is pretty small. But if the model guessed 0.1, whoa, that's a huge error. This lets the model make adjustments that are actually proportional to how wrong it was. The bigger the blunder, the bigger the correction. It just makes sense. Okay, so the model makes smarter proportional updates. We get that. But how does it know which direction to change things in? Which knobs to turn? Well, this is where the actual mechanics of learning come into play, and it involves two key ideas: cost functions and gradient descent. First up, the cost function. Honestly, the easiest way to think about this is as the model's overall mistake score. It looks at every single prediction the model made across all the training data, compares them to the real answers, and crunches them all down into one single number that tells us, here's how badly you're doing. And the goal of training? Simple. Get that number as low as you possibly can. And how do we lower that score? We use a brilliant algorithm called gradient descent. The best analogy, seriously, is to imagine you're a hiker blindfolded on the side of a mountain, and your goal is to get to the very bottom of the valley. What do? Well, you feel the slope of the ground right where you're standing, and you take a small step in the steepest downhill direction. You just keep doing that over and over, and eventually you'll find the bottom. Gradient descent does exactly that with our mistake score. So the whole learning process really just boils down to this simple loop. The model grabs a training example, makes a prediction. Then it calculates how wrong it was for that one prediction. Based on that mistake, it just nudges its internal settings a tiny bit in the direction that would have made that mistake smaller. And then it repeats this thousands, maybe millions of times, getting a little bit smarter with every single step until that overall mistake score is as low as it can go. Now, this is all fantastic for yes or no questions, things like, is this email spam or not spam? But what happens when you've got more than two options? That's when we need to upgrade our toolkit for what's called multi-class classification. So here's the fundamental difference. Binary classification, like just judging a movie review as positive or negative, only needs one line to separate the two categories. But multi-class classification, like giving a rating from 1 to 5 stars, that needs multiple boundaries to carve up the space. To handle that, we swap out our logistic function for its bigger, more powerful sibling, the softmax function.
The softmax function is really the secret sauce for handling multiple classes. Here's what happens. The model calculates a separate score for every single possible category. Softmax then takes that whole list of scores and magically transforms them into a proper probability distribution. Each class gets a probability, and this is the cool part, all of those probabilities add up perfectly to 1. So now the model can say something like, okay, I'm 60% sure this is a 5-star review, 30% sure it's a 4-star, and maybe 10% it's a 3-star.
Look, logistic regression is clearly a massive step up from the perceptron. It's powerful, it's elegant, and it's used all over the place. But like any tool in the toolbox, it is so important to understand not just what it can do, but maybe more importantly, what it can't.
All right, so the strengths are pretty clear. It learns smoothly with those soft updates, which is why it just about always crushes the perceptron in a head-to-head comparison. And because its cost function is convex, remember our blindfolded hiker? Well, that convexity guarantees our hiker will find the absolute bottom of the entire valley, not get stuck in some little ditch halfway up the mountain. But here's the big but. It is a linear classifier. And what that means is that no matter how smart it is, the line it draws to separate categories is always a straight line, or a flat plane if you're in more dimensions. And that leaves us with a really fascinating question to chew on. We've built this much smarter classifier that can learn in shades of gray, but its entire view of the world is limited to straight lines. And we all know that real-world data is messy, complex, and full of curves. So the next great challenge is pretty clear. How do we break free from those straight lines and teach a machine to finally see the curves? Well, that's a story for another time.